Welcome to On the Spot STEM. Today we will be tackling the 2019 Aime I problem number 11. And the problem reads, in triangle ABC, the sides have integer lengths and AB equals AC. Circle omega has its center at the incenter of triangle ABC. An X circle of triangle ABC is a circle in the exterior of ABC that is tangent to one side of the triangle and tangent to the extensions of the other two sides. Suppose that the X circle tangent to BC is internally tangent to omega, and the other two X circles are both externally tangent to omega. Find the minimum possible value of the perimeter of ABC. So the key to these problems, of course, is drawing a very precise diagram, and I've drawn a diagram with a couple of useful lines down here. So as you can see, we have triangle ABC in the center, and we have the three X circles, IA, IC, and IB, surrounding the triangle, tangents to sides BC, AB, and AC, respectively. I've also drawn lines AIIA, CIIC, BIIB. These 3 points are collinear as a function of the in-center x-center lemma, which I will leave a link in the description for. And as you can see, the line AIIA hits circle omega, which I've also drawn at this point down here, which we will label as W. So we can also see that we have some tangency points of the X circles IC and IB. So let's label this tangency point down here to be X, this tangency point down here to be Y, and let's also label the tangency point of the in circle of triangle ABC to side BC as Z. So now we have points to work with, and now we have to think about how we want to solve the problem. So essentially, we want to find some information about the sides of ABC. And the interesting part about this problem is not really the in-center or the X circles that are involved. It's actually the circle omega, which turns out to be tangent to these various circles. So we would like to find more information about omega. And in what cases for the side lengths of ABC, does this circle omega actually even exist? So a good way to do that is to simply compute the radius of omega in two different ways. So we kind of see a plan of attack. We can compute kind of the circle of omega using the line BIB. That's one way to do it. We can see that the radius of omega is simply a subsection of that line. We can also compute the radius of omega as a subset of the line AIA. So we can essentially do that as well. And so let's work on the former part first. So as you can see, we have triangle BIZ. I've blown it up. So basically, let's define some side lengths first. Let's call AB to be A. AC is obviously A. And let's call BZB. Let's call ZC also B, because it's an isosceles triangle, okay? And now, well, we know that BZ is equal to B. And our job is to compute IZ. So let's call the height of triangle ABCH. So then what we can do is, by the angle bisector theorem, since essentially BI bisects angle ABZ, we know that BI cuts AZ into AI and IZ such that AI to IZ is A to B. So therefore, we know that IZ is B over A plus B of the whole length of H. So we can write this as H times B over A plus B. That's the proportion of AZ that IZ is. So now we analyze triangle BIBY, looking for a similar triangle. So I defined X as the tangency point of IC to BC, and similarly Y of IB. And since they're tangency points, we know that these are perpendicular. So what we can do now is use an interesting property of the x circle, which is that by and cx are actually the semi-perimeter of triangle ABC. So I'll leave a link to prove that in the description. It's not very hard. It simply uses the fact that essentially CY and this other point up here, note that it's not A, C, call it M. C, Y, and CM are equal, and you can essentially analyze the tangency lengths to find that theorem in essence. So now we're going to draw triangle BIBY below. So these are our similar triangles. So we want to find this length, which I'll call big R, and we know that this bottom length BY is equal to the semi-perimeter of triangle ABC, which is A plus B. So now we can break out similar triangles in order to find R. So what we have is that H times B over A plus B over B equals R over A plus B. So interestingly, so this is from IZ over BZ equals IB Y over BY. So this is what we have. And interestingly, things cancel out. And we find that, moving down here, H over A plus B equals R over A plus B, which implies that H equals R. So this means that this length is H, this length is H. And although it's already shown on the diagram, you would have to prove that, I mean, we just proved it, that ICA and IB are now collinear, which is very nice. And we obviously know that H by the Pythagorean theorem is root A squared minus B squared. So this is an interesting fact to see. And so now we should try figuring out the radius of the X circle IA. So this is a little more challenging task, but it's fairly doable, I think. So I'm gonna redraw this down here. This is just simply triangle ABC. I'm drawing this for a reason. So we have our X circle down here. And let's draw the in circle actually. And this proof kind of hinges on our in-center, x-center lemma. So let's draw this radius here. This radius, we've already shown before that it is equivalent to H times B over A plus B. This is just simply the in radius of triangle ABC. So, and if we draw this, this is IA down here. If we draw that, that's also perpendicular. And by the in-center, x-center lemma, A, I, C are all collinear. So let's make that a little more clear. There we go. And now we can clearly see similar triangles. Let's call this tangency point N. We can see similar triangles ANI and ABIA. These triangles are clearly similar. Now we can use the property of similar triangles to figure this out. So easily we know that AN is going to equal to basically S minus A, right? This is equal to it's going to equal to S minus 2B. That's simply another fact of the in-center. But I think it's probably easier to use AI. AI is equal to H times A over A plus B. This is simply from the angle bisector theorem that we showed before. And so what we want to try to do is compute AIA in terms of the height and the radius. So we can write similar triangles we want to use is NI over BIA equals AI over AIA. So breaking this out, NI is simply equal to the radius we found before. This is H times B over A plus B. And what's BIA? BIA is the radius we want to find. We call that R. We'll call that little r. We've already found AIA, which is H times A over A plus B. And now we look for AIA, which is simply H plus R. All right. So now we can break out our similar triangles ratio here and simplify it a little bit. So the h's cancel out from both sides. And so rewriting this down here, RA over A plus B equals H plus R times B over A plus B. And our job is to solve for R. And so basically we can move the R term to the essentially the left hand side and keep the H term on this side. So we get that R times A minus B over A plus B equals H times B over A plus B. So now we can clearly see that, so simply getting rid of the denominators, that R equals HB over A minus B. So this is going to be useful for us in the future to compute the radius of circle omega in two different ways. So we're going to start that, but we'll likely need another part of the video. So thanks for watching and stay tuned for part 2. So continuing forward, we need to compute the radius of omega in two different ways, and I've written out the two ways that we've discussed earlier. And so let's try to compute these two values and then finally solve our equation for r omega. So in essence, let me relabel B here. There's B right there, the midpoint of the mid-length of side length BC. And let's do the first one first, namely this expression. So 2RIA, well, we can compute this fairly simply. We computed RIA in the last video at the very end. So we can rewrite this as 2HB over A minus B. And then that would be 2RIA plus RI. RI can be written as the area of the triangle over the semiperimeter. The area is simply HB, and the semiperimeter would be A plus B. So as you can see, we have a very concise expression for R omega for the first expression. It's going to be the left-hand side. And now let's do the next expression. This would be BIB minus BI minus RIB. So let's take a look at BIB. So if we look at it, BI is simply just a subsection of BIB. So using similar triangles, we can actually simplify this expression at hand. So what we can do is note that the ratio of BI to IB is also the ratio of RI to RIB. So let me write that down. We have that the ratio of BI to BIB equals the ratio of RI to RIB. Well, RI, as we all know, is HB over A plus B. And RIB, which we computed before, is simply H. This is B over A plus B. Now with this expression, we can actually compute the subtraction up here, because we can simply rewrite this expression as 1 minus b over a plus b times bib minus rib, which is the remaining term. And this is simply a over a plus b times bib minus rib. Now from here, we look at what is the value of rib. Well, the value of rib is simply the radius of these huge x circles on the side. And this is just equivalent to big R, which is equivalent to h. We can simplify this into a over a plus b bib minus h. And now we're just left to compute bib. Bib, as we look over here, is basically the hypotenuse of the following triangle, a triangle with legs h and other leg a plus b. So we can simplify this, and we can write our final expression using the Pythagorean theorem as a over a plus b times the square root of h squared plus a plus b squared minus h. And now we're finally ready to finish up the problem. So what we can do is we can set this expression equal to what we got before. So this expression can be moved down here. So we can rewrite it. So we have 2hb over a minus b plus hb over a plus b equals the expression we just derived. And now we can really break out the algebra. So let me zoom out a little bit. So now it's time to break out algebra. And here we have to note that h equals the square root of a squared minus b squared. So that's how we defined h at the very beginning of the problem. And so let's take a look. So what we want to do is basically leave in, we don't want to simplify the left-hand side because it has all the square roots involved. So what we want to do is keep the h in as long as possible before we have to, kind of get rid of it. So what we can do is kind of maybe simplify the square root there a little bit. So we can do that. And it's nice that we have h squared. So h squared would be a squared minus b squared, and we're adding that to a plus b quantity squared. So we note that the b squared terms would cancel out, but we would be left with a 2a squared, and we would be left with a plus 2ab minus h on the right hand side there. And basically our left hand side will stay the same for now. So we can finish writing out this expression. And so from here, we should think about what we want to do next. So in essence, what we can do is we can multiply both sides by a minus b times a plus b. And by doing that, we can get rid of all our fractions. So this first term will be 2hb times a plus b. And this term will be hb times a minus b plus, equals a times a minus b times the square root of 2a squared plus 2ab minus h times a squared minus b squared. So this is becoming a very large expression, as you can see. So what we can do now, for the sake of simplicity, we can actually let b equals 1 and then compute the value for solely a, and we can scale up later. So basically we can go through the whole expression and set b equals 1. So if we set b is equal to 1, you would get 2h times a plus 1 plus h times a minus 1 equals a times a minus 1 times the square root of, this would be 2a squared plus 2a, and continuing the expression, minus h times a squared minus 1. And we note that we have a new definition for h, which would be square root of a squared minus 1. So we look for any way we can cancel something out, and we can we can kind of expand out the left-hand side into 3ha plus h equals a times a minus 1 square root of 2. Let's factor the inside. We'll see why this is helpful soon. Minus h times a plus 1 times a minus 1. So our goal here is to basically try to square both sides elegantly. So the nice thing is what we can do is we can move this circled term to the left-hand side, and hopefully after that we can square both sides. So we note that this is, if we expand this out, so actually let me leave this out in expanded form. So this was minus h times a squared minus 1, so it's going to be minus h a squared plus h. And nicely, this plus h cancels with the plus h on the left-hand side. And we can, moreover, move the minus h a squared back to the left-hand side and factor out an a. And this is where things really start to collapse. So a times 3h plus ha equals a times a minus 1 times square root of 2a times a plus 1. So we cancel out the a nicely. And now we're ready to square both sides. And the nice thing is, since we have an h, kind of all the h terms are on one side, we can finally substitute in what we want at the end. So now we square both sides, and squaring both sides, so I'll just write square sides. And so on this side, what we're going to get is a squared minus 1, that's the h squared portion, times a plus 3 squared equals a minus 1 squared times 2a times a plus 1. And the nice part about this is that the a squared minus 1 helps us cancel. So in essence, we can cancel out one factor of a minus 1 and one factor of a plus 1. And so the left-hand side collapses into a plus 3 quantity squared equals basically this term goes away and one of the a minus 1s goes away. So we're just left with a minus 1 times 2a. And this is so much simpler than what we started with, so we're definitely delighted. So a squared plus 6a plus 9 equals 2a squared minus 2a. And bringing everything to the right-hand side yields a squared minus 8a minus 9 equals 0. And looking for the positive root, we have that a is going to equal to 9. So if a equals 9, then what does b have to equal? Well, we set b equals to 1 at the beginning. So that means what we've produced, in essence, is a triangle ABC that looks like this. We've produced a triangle that looks like this. ABC. And remember, b was half the length. So this would be 1, this would be 1. The whole thing is 2. And these are 9. And remember, the original problem statement, if we go all the way back up, asks for, we need the side lengths to have integer length. So let's think about it. If we have a triangle with side lengths 9, 9, and 2, can we divide this by some other integers so that the side lengths still stay integers? Say if we try dividing this by 2, what'll happen is the legs of the isosceles triangle will become 4.5 and 4.5, which violates the conditions of the problem. And we can't divide it by anything else. So this is actually the minimal triangle that we can have. We could obviously have 18, 18, and 4, but we want the minimum possible perimeter. So this is the minimum possible perimeter. All we have to do is do 9 plus 9 plus 2. 9 plus 9 plus 2, which is 20. And we are done.